The Institute of Structural Materials is based around the microstructure property relations of high-performance materials. We're interested in mechanical characterization, mechanical testing of different materials.
We have a wide range of mechanical test frames here that can do all manner of different things, such as fatigue testing, creep testing, thermal mechanical fatigue testing, powder interlayer bonding, and that's unrivaled across the world. And we're quite fortunate all these facilities are under one roof.
It combines a commercial test house, which is called SMART, and also we have a number of academics and research students who can then interpret the results that are generated from the test house.
We've got a track record of success over a number of years and have delivered research programs in aerospace, automotive, nuclear, and even sport.
Here at the Institute of Structural Materials, my research focuses on thermomechanical fatigue, typically of aerospace alloys. So TMF is an extremely complex failure mechanism, and it typically exists when you've got thermal and mechanical strains acting on a material or a component. It consists of fatigue, creep, and oxidation or environmental damage mechanisms. In conjunction with this, we also have an array of different non-invasive measurement techniques for temperature and in situ analysis. These are pyrometry, thermography, digital image correlation, and acoustic emission. All combined gives us state-of-the-art test setups that can deliver accurate and repeatable test results whilst generating a wealth of information that can be analysed post-test to really understand what's going on in the TMF mechanism.
Powder interlayer bonding, we call it PIB for short. You have a powder interlayer on the faying surfaces of the test pieces or geometries to be joined. The powder will fill any asperities and so helps make the joint. When we've created the powder interlayer joint, the first thing we have to do is section it then and check that the microstructure through is sound. So we would use the scanning electron microscope to analyse the joint, and it'll give you information about the crystallography of the metal that you're analysing. And then you would use EDX to check that you had no foreign bodies or a chemistry that there was too different to the parent material. So we use a range of sort of characterisation techniques to check that the bond line itself is of good quality.
So my research predominantly focuses on two main elements, which are mechanical characterization of additive materials, but also realizing the potential of small-scale mechanical test methods. And one such test is the small punch test, where a small miniature disc sample is deformed by a punch indenter under a specific type of loading conditions. So it can be under a tensile type loading, where the load on the punch is subjected to the specimen under a constant rate displacement. It can also be used to induce creep type deformation on the material under a constant load, and also fatigue type loading under a cyclic load. And in each case, the disc deforms in an evolving biaxial manner, and the test technique has previously found use in determining the mechanical properties of highly localized regions, such as interfaces, coatings, weldments, and of particular interest here, materials with changing or non-uniform microstructures, such as additive materials. It's also found use in remnant life assessment of power plant components and ranking the properties of novel experimental materials. So the test technique can be used for multiple applications and needs.
Historically, we did a lot of work on titanium-based alloys, and then we've more into nickel-based alloys for sort of hot section components within aerospace. Now we're starting to get interested in higher temperature materials as well, like ceramic matrix composites.
So CMCs generally consist of continuous fibres or whiskers within a ceramic matrix, and this gives us a real benefit over their monolithic counterparts, namely their brittleness. And we want to use these materials in industry due to their brilliant specific strength and ultra high temperature capability, and they also have brilliant thermal properties as well. So there are a number of advanced techniques we can use on CMCs to understand damage and characterization as we use these materials. For instance, we can use something called acoustic emission, because these materials in nature make noise when they're damaged, and that emits elastic waves, and we can analyze those waves for damage, and then we can sometimes determine what that damage represents, whether it's a matrix crack, fiber failure, interface debonding, and also we can use techniques like XCT or X-ray computed tomography which will give us an internal map of everything within the materials, and we can use that to understand damage and how damage evolves throughout these materials usage.
The ISM's influence in the field of materials testing will continue to grow into the future, as we're extremely lucky to have a great cohesive academic team who works as a unit towards a common goal of innovation and breakthroughs in the world of materials science.
The thing I enjoy most about the ISM is the diversity of the research and the freedom that I'm given to explore my own ideas and follow my own research interests.
With our advanced facilities and characterisation methods, we can adapt to the challenges that future materials are going to bring us.
We've got a good understanding of what we can and can't do, and we're looking at new applications, new collaborations all the time for techniques that we're developing.
So I think the future is very bright for the ISM because we have that experience, we have that knowledge, and develop methodologies for evaluating future materials that are going to allow us to provide ever more confidence for their in-service behaviour.